My name is Simrithi Muralidhar, and the topic that I'm going to be explaining are integrals. What are integrals? Integrals are a topic that are pretty integral or very important to the study of calculus, which is a kind of math. Essentially, integrals tell us how to find the area under a curve. What does that mean? Let me show you. Let's picture a curve on a graph, kind of like this one. We've got our y-axis, we've got our x-axis, and we've got a curve. And I want to find the area underneath this curve. Why? There could be a million reasons. There are tons of real-world applications for integrals, but today we're going to learn how to find it. Okay, I want to find the area under this curve. Now, usually, how do we find the area of something? Like a rectangle, for instance. We take the width and we multiply it by its height. Now, let's say we have a figure that's a little bit more complex. What we would usually do is cut it up into a bunch of different shapes that we know how to find the area of. For instance, we could cut it up into different kinds of triangles and rectangles, and we know how to find the area of these things, and so we find the separate areas and we add them all together. That is how you find the area of a composite shape. But this seems a little too daunting for that. Look at how smooth the curves are, and it's going up and down, and it's just super rough and jaggedy, but it's not clean enough to the point where we can cut it up into different shapes that we know how to find the area of. So we need integrals. So what is a shape that you and I know how to find the area of? A rectangle. We know how to find the area of a rectangle. It's just the length times the width. What if we cut this up into a bunch of different rectangles? I'll show you. Be right back. Boom. We have cut this up into a bunch of different rectangles. Perfect. Now all we have to do is find the area of each little rectangle, add it up, and boom, we have found the area underneath the curve. Right? Not quite. So as you can tell, the width of each of these rectangles is what we call this delta x, and the height is what we call this h. But if you look a little bit closer, you can see that there are actually these little gaps where the rectangle goes maybe a little bit above the curve or a little bit underneath the curve. So this is definitely not super accurate. What do we do now? Well, let's think about it. These are, maybe medium width rectangles. What happens when we make them a little less wide? What happens when you make the rectangle skinnier? Let me show you. Boom. This is an example. So up here we have this curve, and you can see that we have these three rectangles that are of pretty wide width. Now these go really, really high, and there's definitely a huge amount of error here. There's clearly not enough, it's not really specific enough, it's not accurate enough here. But here, with a lot of skinnier rectangles, we can tell that it is a lot more closer to the shape of the curve, and that our curve is actually being more accurately reflected when there are thinner rectangles. Now let's go back to our example. Here, we could just keep it like this, or we can make the curves, or the rectangles, even skinnier, and go skinnier and skinnier and skinnier until what? Until we have infinitely many rectangles. That is a big number. Infinite is infinite, but it is possible with a different calculus topic called limits, which I will not be explaining. But that is how we find the area under a curve with an integral. We make a bunch of different rectangles, infinitely many rectangles, find the areas, add them up, and find our total. That is an integral. Thank you.